Welcome. We would like to introduce you our work, which was improving tunnel mode efficiency of a combined azimuth raster. My name is Gregor, and I would like to introduce you quickly what was our goal and what was our task. What is azimuth raster? Azimuth raster, with azimuth raster, ships make propulsion and steering, so you can manipulate with the ships basically. And combined azimuth thruster, which is specific kind of thruster, has two operation mode: open water mode, which is used most of the time of the ships, and tunnel mode, when the thruster is retracted back and can be used in the shallow waters. The problem of current design is that the efficiency is good in the open water mode, but it's not satisfactory in the tunnel mode, especially in the reverse direction, because some flow is leaking in the bottom well, or there is circulation of the flow. We did a background research in the topic, and to understand better the behavior, we create a 2D simulation in two perpendicular planes. In the left side, on the picture, you can see that in the horizontal plane, there is no problems at all. But on the right picture, in the vertical cut, you can see that there are some problematic places where the flow is leaking or is not as we would imagine, or there is some circulation. We did some improvements to the construction and use a combination of static structures and movable flap. The flap is open when the thruster is in the open water mode, and close the bottom well when the thruster is retracted back. And together with the static barriers makes the flow continuing and avoid the circulation or the other not wanted things, not things we wanted. We simulated the behavior of this with CFD simulations, and Janne is going to tell you something about that.
So, okay, here you can see the initial forward flow of the tunnel. It looks really good on this point. Some small circulation in the upper part, but then on the backward motion there is much more turbulent flow on the tunnel, and it circulates quite a lot. But here, when the same thruster and tunnel is closed underside and nothing else done, you can see what is really circulation around. So it circulates the flow and nothing more of going to the tunnel. And here you can see results forward, and we got some improvement, but it sucks quite a lot from underside. But the flow is going to the tunnel, and its efficiency is about 95% on this. But here we got some much better improvements to the backward flow, and now it's almost efficiency is 90% this way. It was in the initial, there was only 64%. So here you can see on the initial forward simulation and the final forward simulation. And this was a backward simulation, and it was really bad in the initial phase. You can see there is a circulation on the upper part, also quite a lot of turbulent flow on the tunnel to the upper part. And the final result was really good when there is even chamfer there. And here are the results. So the forward velocity was quite good, almost 90 in the initial phase. These blue ones are initials, and then we got some 5 cubic meter flow more on the forward velocity, and the reverse velocity we got much more, from 65 to 82. And Alpo is continuing the tests of tunnel.
To validate the simulation results, we made a model in scale 1 to 20, cut from foam and epoxied. Model was driven by cordless drill, and we measured thrust and consumed electric power with sensors connected to Arduino. Thrust was measured with a strain gauge, current with a Hall effect-based sensor, and voltage with a voltage divider connection from battery to Arduino. Then from power consumption and thrust, we can calculate efficiency. Space needed for our setup was bigger than a cubic meter water tank, but the Aalto Marine Lab was closed due to pandemic, so we had to rig experiment set outside. It was pretty cold and windy in Otaranta, and due to technical difficulties, we did not get results to compare with simulation, but we did get some good experience in field tests. Team Tunnel Flow sends you warm greetings. Bye.